So once again, I welcome you to this online class. Um, in this class, we are going to see about duality and duality in linear programming problem. Just to have the connection between, in our last class, what we have seen. So we have started our linear programming problem. So to formulate the problem first, and then we have seen about solving the problem using graphical method. And in continuation to that, we have seen the one more method, which is called the simplex method. So um, there are again some one more method that is to be that can be used to solve the linear programming problem, which is called as a revised simplex method. Maybe in our physical classes, let us see some more example problems in simplex method and also about revised simplex method. So for this class, so I have taken the next topic, okay, in the module about this duality in a linear programming problem. So comparatively, when we compare with the other models like graphical method and the simplex method, this duality method seems to be very simple comparatively. Seems to be very easy as well. So only thing is, we will be having some, for every problem, there will be some duality for a particular problem. That is what we have to understand. So there is a logic behind it. So here we are just creating a duality for a particular problem, for even for a better understanding. By the name itself, we can understand dual means it is something we can take into as a duplicate one, or a second one, right? We will have some two set, right? So we can have different meanings. Likewise, in linear programming problem, whenever we are talking about a duality, then we are considering that for every given problem, we can construct a duplicate or a dual of that particular problem. That is what we have to understand. And again, I'm going to give you one more term, which is called this primal problem. So please take a note of it. Whatever topics that we have seen so far, or whatever problem that we have seen so far. Okay, so the given problem is known as the primal problem. Okay, I repeat again. So whatever problem so far, I think so far we have seen maybe some 6 or 7 problems. So the given problem is called as the primal problem. Okay. So for that problem, we can able to write a duality for that. So we call that as a dual problem, right? So on the whole, we can call this as a primal dual relationship, right? So we can have a primal problem initially, and then we can rewrite that problem into its dual. So we call this as a dual problem. All right. Fine. So here there is one small statement given here. Maybe you can take a note of it, right? So here a shadow price has been given as a definition. That means it is the rate of change in the optimal objective function with respect to unit change in the availability of a resource. All right. So here we are talking about the objective function and also the availability of resource. So on the whole, shadow price will be equal to change in optimal objective function value divided by unit change in the availability of resource. So this is what a basic formula that we can understand about any constraint. So to be more precise, for any constraint, we have this shadow price. Moving on, as I said, we have to understand the essence of this duality. So every linear program has another linear program associated with it. So it is the dual problem. And more importantly, as I said, the dual complements the original linear program, which is the primal. So that is what I told you. Whatever given problem is known as the primal one. Then for every given problem or for every linear problem, they have another linear one which is associated with it. So that we call that as a dual one. So the theory of duality provides many insights into what is happening behind the scenes. So I want all of you to take a very note of it. So here in the left side of the column, you can see a primal format, and in the right hand side, you can see the dual format. Okay. So in the left side, you can see the given objective function, which is maximized in this case. So maximize z equal to the objective function, okay, subject to the constraints. So there in the constraints you will have the list of constraints. Now how this primal problem is being converted into its dual. So here you can see the transformation transition that is taking place. So here whenever I am writing my given primal problem into dual, if it is given as maximization, the first step I will convert this into minimization. So minimize, I can use some other variable instead of z. I can use some other variable equal to the objective function will be converted into a different one. Um, See, I think you can see here. Now you can see some of the arrow marks here. So this is our given primal problem. Now this has been transformed into its dual. Now this is our objective function. Now the objective function has gone to the constraints part of the dual problem, and again the constraints or the resources of the constraints are, that has been taken to the objective function in the dual. I repeat my statement again. When I am converting my primal into dual, the objective function has been taken to into the constraints part, that is in the right hand side, which is the resources. So that has been taken here. And then the right hand side resources in the primal part, which is in the constraints, okay, that has been taken here in the objective function of your dual. Okay, so I think you are getting the point. Maybe if I am showing you any example, then you can understand even better. And similarly, we will have some rewriting in our variables like row wise or column wise. So when we are rewriting that, then we can able to transform the given primal into a dual. So this is something a general format, which is the primal dual relationship between a pair of linear programming problem. So here you can see something even better. So here the decision variables are, the given decision variables are x, but here we will be converting that x into y when we are writing our dual. Now, in our given problem, if the problem is maximize z equal to the objective function, so that will be converted into minimize. So we are using a different variable called as w is equal to the right hand side values. And similarly, subject to the constraints that will be taken in a different format. I will show you in a problem. Right, now we'll just consider this a small problem. So you have to understand the primal part, which is the given problem. So the problem will be given like this. Then we will be asked to write the dual for the given problem. So this is the given problem. So that problem is called as primal. So how are we rewriting it? So as I said, so maximize will be converted into minimize. So we are again taking the z or z into w. Now, please look into it. So, in our given problem, the resources which are the right hand side of the constraints, so that are taken to the objective function here. So you will take 4 plus 12 plus 18. Okay, so that values have been taken to the objective function. And again, more importantly, our variables have been converted into x into y, as we have seen in our previous one. So decision in the given problem, the decision variables will be x and the dual decision variables will be y. So similarly, we have seen here. So now we are taking 4y1 plus 12y2 plus 18y3. So this is our the objective function in terms of dual. Now, subject to when we are writing our constraints, again, it is very easy to understand. So, in our primal problem, it is given as x1, which is less than or equal to 4, and then the second one, and then the third one. Now, what we are going to do here is we are just taking the values in this way, and that will be written as a row. I repeat again, we are just taking something like a column wise here, and then we are converting that into a row wise. So here our column wise here is x1, and here in the second row we don't have x1, and in the third row we are having 3x1. So that will be converted into y1 because our dual decision variables are y. So we are taking y1 plus 3y3. I repeat again, y1 plus 3y3. So that is our first constraint. Then the second constraint is uh, again we don't have x2 here in the first equation. So we are going for the next row, which is 2x2, and in the third row we are having again 2x2. So when we are writing this column into this row, then we will have 2y2 plus 2y3. Okay, now we'll come to the right hand side. So here in the given problem, the right hand side has been taken to the objective function. Now the objective function of the given problem will be taken into the the resources in the constraints. So you can see y1 plus this 3y3, this less than or equal to will be converted into greater than or equal to when we are writing it into dual. So y1 plus 3y3, which is greater than or equal to 3. Similarly, the second equation, 2y2 plus 2y3 is greater than or equal to 5, where y1, y2, y3 is greater than or equal to 0. So I hope you are getting the point very clearly. So this is very simple to understand how we can convert our primal problem into dual problem. Only thing is we are just rewriting by following some rules and regulations of this primal dual relationship, right? So in the coming slides, you can see some of the rules that we have to follow and also to understand. Fine. So the same primal dual problem can be written in matrix form as well. So you can see the matrix here. The maximization has been converted into minimization, and then similarly your x1, x2 will be taken into y1, y2. All column wise will be taken into row wise. All row wise will be taken into column wise. The same structure, but we are writing in a matrix format. That is what primal dual in matrix form. Fine. So here there are some rules given for constructing this dual problem. I'll just quickly read some of the important points so that you can follow the same. So here the rules for constructing the dual from the primal and the vice versa using the the symmetrical form of this linear programming problem. So the first rule is a dual variable is defined corresponds to each constraint in the primal linear programming problem and the vice versa. So for a primal LP problem with m constraints and n variables, there exists a dual LP problem with m variables and n constraints. That is what we have interchanged the values. I think you would be remembering that. So we have rewritten the values like taking all the rows into columns and all the column variables or values into the rows. That is why it is taken as m constraints and n variables will be converted into n constraints and m variables. Okay, so please understand. And then comes the right hand side. So the right hand side constants, which are b of the primal problem, so that will become the coefficient of the dual variables. Okay. So as I said, in the primal problem, all the right hand side, our resources, which are called as b values. So all the b values will become the coefficient of the dual variables in the objective function. All right. Right. Then the coefficients of the primal variables in the objective function, all right, that will become the right hand side constants in the dual LP problem. So please understand, please remember these rules. Uh, then for a maximization LP problem with all less than or equal to type, there exists a minimization dual problem with all greater than or equal to type and vice versa. So you can take, so whenever we are having our maximization as a primal problem, that will be converted into minimization, and our inequality type will be greater than or equal to in terms of dual when coming to as a minimization problem. Again, the matrix of the coefficient of variables in the constraints of dual is the transpose of the matrix of coefficients of the variable in the constraints of primal and the vice versa. Okay. Now, if the objective function of a primal LP problem is to be maximized, then the objective function of the dual will be minimized. So that we have already seen. So in a given problem, if the primal is maximized, then the duality will become minimized. Okay. Then if the ith primal constraint is equal type, then the ith dual variable is unrestricted in sign and vice versa. So whenever we are having some equality type, so this rule exists there. Okay, here there are some more problems given here. So we can again rewrite based upon the based upon the given primal problem. So the primal problem can be converted into its dual problem by following the rules that we have already seen. So I'll just quickly move forward because these are all some of the examples given. Maybe if time permits, we'll just see all those examples in our physical class. Okay, I'll just quickly go through. Again, some obtaining the dual problem. So whenever we are seeing the vice versa as the word in our rule, you can have the both the cases. Either it can be maximization or it can be minimization. You can see either the case. Fine. Now, in addition to those rules for duality, there is one more topic called as duality theorem, right? So this theorem is again the possible relationships between the primal and the dual problems. We call this as a duality theorem. Okay. Now here you have to understand about some of the situations where it comes around. Okay. So if one problem has feasible solutions and a bounded objective function, that means when we are having some bounded objective function which has an optimal solution. Okay, so both the weak and the strong duality properties are applicable. Okay, now if one variable has feasible solution but an unbounded objective function, that means there will be no optimal solution, then the other problem has no feasible solution. So please see, these are some of the default one that we have to memorize and then keep it in our mind, because theorem is something we have to write as such. Then if one variable has no feasible solution but then the other problem either has no feasible or an unbounded objective function. Okay, so this is our third situation. Then comes the the solutions or the complementary solutions. Okay, where we can have this primal feasible, then the primal optimal. Okay, based upon this dual primal relationships. Okay, so I'll just go to the next slide. This is a pictorial representation of primal and dual. All right. So again, I'll quickly go through the previous slides for you to just recall about this primal dual relationship. Okay. So we have seen what is this primal dual. This is a general format that we can write about primal and dual. So we will have our decision variables in the given problem as x, but when we are writing, we'll convert that into y. That will be the decision variable for dual. So when it is maximization problem given, then that will be written as minimization as a dual one. Then we can even change the variables, and then all the row-wise structure can be taken into column-wise structure. Column-wise structure can be taken into row-wise structure. So that is what I have taken here. So in the problem we have seen the coefficient of our objective function has gone to the resources on the right hand side in the dual one. And similarly, the right hand side or the resources in the primal have been taken to the coefficient of the objective function in the dual. Okay. Then inside the constraints, all our the values which are in the column wise are taken into row wise in the dual. Okay, so that is the point we have to understand. Then please remember the rules for constructing this dual problem, and then okay, there is again okay, based on the rules, you can see all these rules in one single table. Okay, then there are some example problems given. So in our maybe in our physical class, we can again see some problems how we can construct our primal into dual. Then we have seen about this duality theorem. So you have to understand. Then you have to remember the theorem in terms of um, this primal dual relationship. Right. Again, I think I have missed one slide. Here we have one weak duality property, and another one is strong duality property. So you can just have a look on it. So if it is a weak dual property, then if x is a feasible solution to the primal and y is a feasible solution to the dual, okay, that means our given problem is less than or equal to our dual problem. Okay, that is what our weak duality property. So when we are calling this as a strong duality means if x is an optimal solution to the primal and y is an optimal solution to the dual, then our both primal and dual will be equal. Okay, that is the point you have to understand. So again, you can see some of the properties here. All right. So with this, our duality theorem or duality process is over. So as I said, we can see some more problems. Maybe whatever problem I have given in the slides, maybe we can take those problems as an exercise when we are in the physical class. Right, moving on, I'm going to the next topic, which is called as sensitivity analysis. Okay, I'll just give you an orientation about what is this sensitivity analysis. Okay, sensitivity analysis is nothing but in the name itself, you can see there is one word called as analysis. That means, as a user, right, we are making some analysis in a given problem. That is what about the sensitivity analysis is all about. So in the very first statement, you can see we can have some optimal solution sensitivity to changes in model parameters. That means there will be a problem given. For instance, we will have some two variable problem, and in the two variable problem, we will be asked to solve using a graphical method. Okay, so I want all of you to take back your memory to your graphical method. All right. So in a graphical method, so how we will be starting our solution, or how we will start to solve. So firstly, we will just try to find out the plotting points inside a graph. So by just putting x1 equal to 0, you will get x2, and then put x2 equal to 0, you will get x1. Similarly for all the constraints. And then you will get the values. You will just exactly plot those values into the graph, and then we will find the feasible solution space, then mark the corner points, and then we will find the values of those corner points, and then putting all the points in the given objective function, and based on the objective function we will find our optimal solution. So this is what the overall process that we have already seen in graphical method. Now there is one more process ahead. Okay, that is what about the sensitivity analysis. So here in the first statement you can see, whenever there is a change in the parameters, okay, then what would be the change in our solution? That is what the sensitivity analysis means. So what are the possible changes that we can make in a problem? That means one possible change could be in the coefficients. That means, for instance, when we are having this objective function is maximized, is that equal to, uh, for instance, 4x1 plus 5x2. So this is the given objective function with some coefficients, right? Now, if our question is being built like, whenever you have a change in the coefficient, like in the place of 4x1 plus 5x2, if we have 6x1 plus 7x2, okay, what would be the solution? Okay, that is what the analysis part takes place. Similarly, in the right hand side, that is what the b values. So so b values are nothing but the resources available. So when there is a change in the resources available, what would be the change in the solution as well? So this is what the analysis that we will be making after completing the solution, after completing the problem, after finding the solution. So if we change the parameters, how does it affect either the feasibility or the optimality? So if it is a feasibility, if it is violated, then it is called as primal infeasible, but maybe dual feasible. So I want all of you to remember these words: primal, dual, primal feasible, primal infeasible, dual infeasible, and dual feasible. Right? Whether it is an if how does it affect optimality? If it is violated, then it is called as dual infeasible, but maybe primal feasible. So these, we can attain, or we can come to this solution whenever we are coming across the situations like increasing the resources or decreasing the resources, making changes in the coefficients. Right, so we can come to these situations. Moving on, some of the general procedure for sensitivity analysis is, first of all, we have to revise the model and then calculate the changes to the original final table, then convert to the proper form using some Gaussian elimination. Then we are just making some tests like feasibility test, optimality test, right? Is the new right hand side is greater or equal to 0? Is the new row coefficients are greater or equal to 0? And then we are doing some re-optimization, like if feasible but not optimal, if not feasible but satisfies optimality, if feasible and optimality. All right, so these are some of the procedures that we have to follow when we are doing this sensitivity analysis. But keep the point very simple. This is just for the theoretical point. We have given some of the points, but when we are solving a problem, it is again easy to solve the problem because initially we will do a regular graphical method process, and then how are we making the changes, and based on the changes, how does the solution got affected? Okay. Is there any increase in the solution, or is there any decrease? What is the difference that has taken place? This is what the overall analysis that we would take place. So, in continuation to that, how does the value of the optimum solution change when coefficient in objective function or the constraints changes? Okay, then why it is important, right? So the coefficients are the limits and constraints may be poorly known. Okay, then effect of expanding the capacity, then changes in cost or selling prices of the products. Then again, we can have the market demand of products vary. Then, for instance, crude oil prices fluctuate. So when we are taking this sort of situation, because every day, the data changes, the value changes. So for making some better calculation, to have some best solution, we have to make some analysis, like taking the previous, maybe the history values, and then if there is any change has occurred, then we can make what difference has been taken place uh, by making some suitable analysis, right? So it is again, this information is readily available in the final simplex solution, and I'll tell you, uh, this sensitivity analysis can be done using a graphical method and also using a simplex method. The procedure is the same. Only thing is your values will get changed. So based on the changes in the value, how you are taking your, how the solution has been changed as well. What difference does it has occurred? That is the final logic that we have to understand. So here there is one example that has been given. So here you can see some of the constraints that has been changed here based upon the given problem, or how we can how the changes has a great reflection or a great impact that has taken place in terms of a solution. So that is what given in the problem. So if there is any change in the coefficient, maybe based upon the profit or based upon the loss, and if there is any change in the resources, then whether it is the resource has been increased or the resources have been decreased. Okay, so based on that, we can do this analysis. You can see this is the given um, model, which is 3x1 plus 5x2. But based upon this, we can again calculate and find the solution for the original model. I repeat again, this is the original model, original problem given. Based upon, we can solve the problem as like a simple graphical method and find the solution for this original model. And then, based on some conditions given in the question, we have to rewrite or revise our model. So now you can see some of the differences that has already taken place. Now here, the profit values have been changed from 3 to 4 in this x1 variable. And then you can see in the right hand side, there is one increase in the resources. You can see that's been converted from 12 to 24. And again, there is one decrease in the condition where you can see this 3 has been decreased to 2. Now, we have to again construct or solve a separate problem or a separate solution For this problem, this is the new revised model. For this model, again we have to do the same graphical method process, and finally we will get a solution for this. Now after that, we have to analyze and see maybe the difference that has taken place from this original model and the revised model, and what will be our conclusion based upon both the solutions. Okay, so here you can see some of the impacts that takes place when there is a change in the coefficient. And again, this is done using a simplex method. I think you can remember the table that we have already constructed. So this is based upon the simplex method. The same sensitivity analysis can be done using simplex method as well. You can have some different iterations, and then we'll see that. Then you can see there is only changes in B. That means if there is changes in the right hand side of the constraints, then what would be the impact that takes place in terms of our solution? So everything is about the same sensitivity analysis, how to uh, find the revised solution. Fine.